and you will have some registers. They are basically 0 and 1. A function is 20% off. If you use any lab sessions, it's not limited to steps. You will convert assembly compiler it into assembly. So, and for the lab assignment, there are Q&A. Okay, so let's start the discussion. Hi everyone, welcome to ICS 51 discussion. I'm Jin, your team, one of the teaching assistants. So before we start, let's talk about some logistics. For lab sessions, there are Q&As, and you can drop by anytime as long as it's the slot for lab sessions. And you can join any lab sessions. It's not limited to the one you are enrolled in. And you can also stay there and do your homework, even you don't have any questions. For the lab project, you have a policy to get 20% off if you submit late, and you'll be 2 days late for each project. And for the lab assignment or the discussion, we assume you know some programming like C programming, but not assembly, because we may use the C program as an example to know how to translate it into assembly. So this is the abstraction to give you some idea where the assembly is. So normally when you start to write your program, the C program, it's like high-level language. The syntax is much more readable for human beings. And through the compiler, through many steps, you will convert into assembly, which is the one you are working on. And assembly depends on the computer architecture you would like to run. If you are working, if a program would like to run on Intel processor, then you'll be the x86 assembly. And in this course, we are working on MIPS processor, so we are working on MIPS assembly. And after having this assembly program, we will use the assembler to convert this assembly program into machine code. They are basically 0 and 1, a bunch of 0 and 1s, which is readable for the hardware. Because I think later on when you are learning the logic design, the hardware, they are gates, and they are all 0 and 1. So the 0 and 1s are readable for the CPU, but not for us. So this is the location where assembly is. And I think after this course, you'll appreciate how easy to code in high-level language compared to assembly program. So let's get some idea, a typical computer architecture. And on the left-hand side is the CPU, it's a central process unit. And you will have some registers. Consider it's like a storage. And you will have some ALU to do some operation like addition, subtraction, or multiplication. And since this is in one chip, so they are much faster compared to the right-hand side, a larger storage, we call it memory. So registers, so because they are in the chip, so they are fast storage. So most of your computation, you would like to do it within this CPU, not related to memory. And in MIPS, we have 32 registers. Each one is 32-bit. So we often call it 32-bit processor. And yeah, so there are 32 of them, registers. So this is a list of registers, and they could be categorized for different usages. And because it's hard to remember a number, so in assembly, you can write with the names. And you can see, for example, if we want to use it for temporary result, we will use the T, and because you have 10 of them, you can use T0 to T9. And for something else like make a function code for the arguments or return value, we'll use these V or A registers for different purposes. We'll talk more about how to use these registers in the future discussion and practice in your lab assignments. So for now, just remember or just use the T registers in your code. So the different categories of using the registers, we call it register convention. So for example, A is used for arguments, function arguments, and V is for the return value, and the T is for temporary result, like intermediate values, and S is for some set variables. And there are some spatial registers outside these 32 registers. They are like high and low. We'll talk about it later. So these are registers. There are 32 of them, and they are fast. And you would like to use it as often as possible compared to the memory. So for memory, they are like a very large storage. And so you can see there are many, for example, it's like a continuous storage. And every time you can have access to one element, to index the element, we use the address to index it. And as we know, the MIPS processor is a 32-bit processor. So the index you can point can range from 0 to 232 minus 1. If you convert it into numbers, it's around 4 giga. It's around 4 billion, so it's 4 gigabytes. So that's the reason you can see there are only 4 gigabytes you can index. But currently in our laptop or desktop, they are much more than 4 gigabytes. So nowadays, the processor we are using are 64-bit. They can index much larger storage space. So for your MIPS, you can only read or write to the memory with 1 or 2 or 4 bytes. So 1 byte is like you read one element, one chunk of it, or 4 bytes. The terminology here is called a word. So 4 bytes means a word. Or you can read half word, so there are 2 bytes. There are instructions that correspond to each access. So just a refresh, the computer architecture we have, the CPU has registers. They are limited, but they are fast. And we have some arithmetic unit to do the computation. And if we run out of the storage, we would like to read or write to the memory. And they are stored, but they are much larger. So let's go more detail about how to write assembly code. Consider this is like a C code. I'm going to do B plus C and assign a value to A. So in assembly, these registers, you will use the registers to hold your variable's value. So in this case here, I assume I have hold my S value in T0, and B in T1, and C in T2. So if I write 8 instruction and T1 and T2, and assign a value to T0, this will do the addition just like the C code and store a value into T0, which is the A. I'm going to consider the A's value. So in general, your MIPS instruction, the format of writing one instruction is you write an operation. Our previous example is like 8 to do addition. And you write operands. So for example, the add, we have 3 operands, 3 registers. And if you want to write some comment, you can put a hashtag, and the rest of them will be considered as a comment. And you can also add a label. So label is for later on when we are working on jump instruction to know where to jump to. We can put a label as a reference to use. So the operations like depends on the arithmetic unit we support. So we can have addition, subtraction, or something else. And the operands depends on the type of operation. The operands could be different. It could be the register name or some constant values. You'll learn more the instruction and how this format later. So for the program, if you want to write a simple MIPS program, on the right-hand side, this is like a C code. You already define some global memory, global data, global variables. You can define some integer array. Then later on, you run to write some functions. So you have 2 parts, one for data and one for code. So in the MIPS, you put some pragma to specify which type of segment you are going to work on. If I put pragma.data, that means I'm going to define some global arrays or some strings, something else. And for the implementation, I'll just put a pragma.text and put a label to use as a reference. And yeah. So for a data directive, if you want to define some global array or some string, you put a directive, the data. And for your coding, you put a text for the marks to figure out the following instructions are for the code. So let's talk about some instructions, some basic instructions, so you get to know how to use it in your lab 1. So you have some like arithmetic instruction or logical instructions, or if you want to copy data between the registers or between memory and registers, or if you want to do some comparison, just like in high level, you do some if-else, if condition, or while, or for loop. So all this can be composed into multiple small instructions here. So let's start with arithmetic instructions. This is the most straightforward. If I want to do the addition, we know the add, and we know there are 3 operands for the addition. You put the register you want to sum up in the source 1 and 2, and you put a register you want to store into in the destination operand. So for example, here we'll do T1 plus T2 into T3. Same with subtraction. And if I want to do some multiplication, so for the multiplication, there are only 2 operands, source 1 and 2, and the result will store into 2 specific registers, which is called low and high. The reason is because each one is 32-bit, and if you do some multiplication, the result will be 64-bit, so you need 2 registers to store the value. And for division, you have the quotient and the remainder, so they are storing into different registers as well. And sometimes when you are doing the addition and you want to add to some constant number, here we call it immediate value. So you would like to use different instructions to do the addition, for example. So if you want to add the T1 with the value of 5, instead of writing add, you should write different instructions, the add I, to tell I'm going to add the second operand with a constant immediate value, which is 5, and store to the destination registers. And if you want to add with a negative number, it's still doable. So just remember, depends on different operation you're working on, you'll need different instructions to execute. So for example, here, if I want to add 2 registers value into another register, I cannot use add I, because add I is used for an immediate value. And okay, so the next will be the logical instruction. So for logical instruction, we learn how the NOT or AND to work in single bit. For example, if it's NOT, that means if the input is 0, my output will be 1. They will be inverted. And because the MIPS are 32-bit, so it will extend to 32-bit. So we call it bitwise operation. So you can see this is, for example, my input. If it was 0, it becomes 1. Each one becomes 1, 0 becomes 1, and 1 becomes 0. And if it's the same with the AND, so the output of AND will be 1 when both of the inputs are 1, and the rest of them are 0. So if you look at this example, T3 and T5, the output will be 1 when both of the bits are 1, and the rest of them are all zeros. So these are more practice if you use different operations, for example, the OR and XOR. So for the OR, either one of the input is 1, then you get a 1 output. And let's talk about the shifting. So for the shift, you can move your bit left or right. So to moving left, you can write SLL. So this is shift left logically. So this will shift your bit. For example, this one, left 3 bit. If I write SLL T0, T0, 3. So the bit will shift left 3 and fill with 0 to it. So I can do left shift. That means I can also do right shift. So if I write SRL, I will do a right shift and pad with 0 to it. And so there's one more instruction called shift right arithmetic. So this will consider the source register's value. So if it was negative number, it will be still negative number. So if you look at the example here, SRA, if I do a right shift 3 bit, it will fill with 1 instead of 0, because the sign bit here was 1. So if you read this as a decimal number, it's still a negative number. If you read the previous one, before that, it was a negative number, but now it becomes some positive. But it's because you are treated as some logical value. So these are just some operations if you want to do addition, or if you just treat it as some binary number to do the logical operation. And sometimes you would like to copy some data between registers, like copy from T0 to T1, T1 to T0. You can use this type of instruction, like a move, to copy from the source to the destination. Or you can just do addition, like add my source with 0 and store into the destination. So they are actually like copy from source to destination. And something like later on, if we want to copy data from the memory into a register, we'll use different instructions. We'll talk about this type of instructions in later discussion. So here I talk about some pseudo instruction. So pseudo instruction is some instruction that is supported by the assembler that is not implemented in the hardware. So it's the instruction that makes your life easier. For example, this move. The move is not implemented in the hardware. It's actually translated into what I just talked earlier, like we do addition, add with 0. There are some more examples we'll see later. So the pseudo instruction is some instruction that, for make your code easier. So for example, this multiplication, we learned left one earlier. We can do T0 multiplied by T1 and store the result in high and low. This is wired in the hardware, so you will always store the value into low and high. But for our usage, we know most of the time our T0 and T1 are very small number, so the result will be basically in the low. The high will be always 0. So that's the reason the assembler will provide a pseudo instruction to just take the low value out into one register. So by writing the right one, you can write MUL, the destination register, and the source 1 and source 2. If you assemble the code, it will actually translate into the MOT, the real instruction, source 1 and source 2, and another instruction to read from the low register and store into destination. There are much more pseudo instructions. You can just use it, but this just gives you the idea. Some instructions are not implemented in the hardware. And something else like syscalls. So in the high-level language, you would like to print the result to the console, or you would like to open a file. And this is supported by the operating system, so it's not any instructions. So in MIPS, MIPS provides this syscall. And to use this syscall, you would like to do the following steps. You put a service number. There will be a list tell you to do what operation you would like to set, what number for the V0. And depends on the service number, you set different values for specific registers. Then after that, you call the syscall. And depending on the service number, you read from the return value. So for example, in your lab 0, you're going to print some decimal value, or you're going to end the program. You set different values for the V0, and you just write a syscall after that. So if you want to know more reference for all the instructions or how the syscall works, you can open your MIPS, and if you press F1, you can see the help menu. There are many informations, for example, the instructions you can use, or the pseudo instruction you can use as well. That will be very useful when you are coding. You can just read the menu to know like what tools, what instructions you can use. And also, when it comes to the syscall, you can also find it in the help menu as well. So this is the MIPS emulator, and we are using MIPS, and also it's used in AutoGrader. So just remember to walk through your Lab 0's project. Okay, I'm going to talk about another one. So previous one is like just introduction, so you know how these instructions to be written and how the structure of the code is. So in this one, we are going to talk about some method, how to apply this instruction to some high-level operations we want. And that could be useful in your lab 1. So we're talking about bit masking and multiply by shift and end, and also conditional statements. So for the bit masking and this multiply by shift and end, we are going to use the instruction that the arithmetic instructions and the logical instructions to accomplish this method. And for the conditional statements, it's like if else, we'll introduce you the comparison and control transfer instructions. So for your part 1, for the swap bit, you probably want to use bit masking. And for the triple range, you will use the if-else condition. And for the last one, the matrix operation, you would like to use bit masking and maybe the if-else condition to implement it. So maybe later you can start to work on the part 1 and part 3 of lab 1. So for bit masking, we use bitwise logical instruction to try to set the bit value to 1, or we can use it to clear some bit, like reset to 0, or we can try to retrieve or query some bit value. And all we need to do is to set a specific mask to work with the logical instructions. So we learned earlier when we use the OR instruction, this is the OR truth table, and consider that 2 inputs and B, you have 1 output. So for the OR, the output will be 1. When one of them is 1, the output will be 1. So if you read the A as your input number and your B as a mask, and if you end your input number with 0, you can see the output's value will be the same as your input. And if you end your input number with max value 1, you can see your output will be always 1. So this could be useful if you want to set specific bit value to 1 and keep the remaining bits as unchanged. So for example, if we only have 8 bits here, we want to set the left 4 bit to 1 and keep the right 4 bit unchanged, we can define a mask. So because we know if we OR with 1, there will be 1. We can put a 1 for each bit we want to set 1, and put 0 to the bit we want it unchanged. So we OR our input with this mask. We can set the left 4 bit to 1 and keep the right 4 bit unchanged. So this is if you want to set some bit, you can use OR and put the corresponding mask you want. So if you want to clear in some bit, we can use AND. So this is the truth table for AND. There are 2 input and 1 output. So again, let's consider the first one as an input number and the second one as the mask. So if I AND my input with 0, you can see my output will be always 0. And if I AND my input with 1, my output will be the same as my input. So that means I can clear some bit to 0 if I AND it with 0. So the example here, we have a bit, then we want to clear the left 4 bit and keep the right 4 bit unchanged. We can use the AND instruction and put a mask because we want to clear the left 4 bit, so we put 0 to it. As we know, we AND with 0, the output will be 0. And we put 1 at the right hand side because we want it unchanged. So by AND with this mask, we can get the output left 4 cleared and the right one unchanged. So if you know if you can clear some bit and rest unchanged, that means you can sort of query or retrieve the value you want. So for example, if I want to query the right 4 bit, I can just simply clearing the left 4 bit. Then the right 4 bit's value will be the one I care. So the example here, this is my input. If I want to query the bit number 3, so the right one is bit 0, bit 1, bit 2, and bit 3. So if I have my bit 3s as 1 in my mask, and I AND with it, I can get my bit 3's value of the input number. So if I AND with the mask, I can see it becomes 1 for this bit, because my input is 1. So to write in assembly, to have the mask with this value, you can count it, it's like 2 to the 3. So you can set your T1 as a mask to be the value of 8. And if I AND my input number T0 with my T1, so T1 now is my mask, and store my value in T2. Then by comparing the T2's value, I can know if the bit number 3 is 0 or 1. So this is to query 1 bit, for example, bit 3. Then you can think about if I want to query more than 1 bit, just like your lab project, if you want to query the R bit, or if I want to query the even bit, you can think about how to build a mask. So we know if we want to query some bit, we use AND. And now our application is 32-bit. And so for example, if you want to query R bit, so this is the even bit 0, and this is bit 1, bit 2, and bit 3. So we care about bit number 1, 3, and 5, and following. So this is the mask value. If we AND with it, then we can query the R bit of my input. And this is binary. And in your assembly, you can only write in hex or decimal number. So you would like to figure out how this convert into hex. For example, here it would be this number. So this can use to query the R bit of your input. So you can think about if I want to query the even bit of my input, how should I build the mask? So yeah, this is how you get multiple bits from your input number. Then we talk about some multiply by shift and AND. So we know we can do multiplication and division. And for multiplication, a basic instruction we can do is mod T0 and T1, like 2 source registers. The result will store in low and high. And we can also use some shooter instruction to get the lowest value into 1 registers. So if you want to do some division, we can put 2 source register and the quotient and remainder will store in low and high registers. Then you can use the follow instruction to read from the low or read from the high. And to do a multiplication in the decimal way, we do this multiplication for each digit and add it together. So if we do it in binary, they are the same. So you can see here, if we have 4 bits number, then we need to do 4 times multiplication and addition as well. And this is quite time consuming. So that's the reason sometimes when you write a high level language and you have a lot of multiplication or division, the performance will drop because the overhead to do the multiplication and division is much higher because it will decompose into multiple instructions. So if you know if you can read this number in binary, and you can do it more efficient. So for example, this is a value of 18 in decimal, and if you write in binary, you will code it in this way. So a value of 18, you can write this in binary, then you can see it's 2 to the 0 and 2 to the 1 and 2 to the 4. So it's 16 plus 2, then it's 18. Then if we do some shifting, okay, so this is an example of 18 we just talked earlier. If you do some shifting, if you do left shift 1 bit, what will be the result? So you can see if we move left 1 bit for every one of them, 1 goes into here, and 1 goes into here. Then let's calculate the result of this binary number. So the first bit is 1, and this is 2, and this is 4. So you can see this is 4 plus 32, and the value becomes 36. So that means if you do a shift left and 1 bit, the value gets doubled. It's more like multiplied by 2. So if I shift more than 1 bit, there will be multiplied by 2 to the power of bit I shift. So if I left shift, it's like multiplying, and if I shift right, it will be equal to if I do the division. So how do I write this in assembly? So previous time we write a mod, and here, if we know we are going to multiply by 2, we can just write shift left logically, just shift left and 1 bit. Then if you want to multiply by 16, then we know 16 is 2 to the power of 2. So if you shift left 4 bit, they will be equivalent to the multiplication of 16. So if you write SL and T2, T2, 4, then this will shift the value in T2 left by 4 bit. That is similar if you do multiply by 16. And you may wonder, if I want to multiply by some number that is not the power of 2, how does it work? So you can do something like, if I decompose it into a multiple power of 2, then sum it up together. So the 18 could be translated to 16 plus 2. Then if I get a value of 16 and 2 and add it together, then I can get a multiplication of 18. So that's the way you can just decompose it into multiple power of 2 and sum it up together. So for example, the 13, it could be like it will be like 8 plus 4 plus 1. If you write a 13 in binary, it'll be very easy to find how you decompose this number to the power of 2. So this is 2 to the 0, and this is 2 to the 1, 2 to the 2. So this is 1 and 4 and 8, just like what we figure out. So yeah, by having some multiplication that is not a power of 2, we can decompose it into a sum of power of 2. Then it will be much faster compared to if you just write multiplication. As we know, if we have 32-bit number, and if you write multiplication for 32-bit, it will be do addition 32 times. Okay, so let me talk about some conditional statement about if-else. So when you are writing assembly program in your code, it will be processed instruction by instruction from the top to down. For example, if your first instruction is add I, you will have start with the add I, and continue to run the next instruction, and continue to run the next instruction. And for the processor to know which instruction that is going to process, they use a register called program counter, the PC register, to keep track of where is the next instruction we are going to process. And for example here, because we don't have any control instruction, so you will just run sequentially line by line. And sometimes in your program, for example, in your high-level language, your code will jump up and down, or you go to make some function call, you jump to another code block. In this case, in assembly, we will use some instruction to jump to some other part of your code. Something like, for example, here, if we don't have instruction to jump, the code will follow at I and end and the following. And if you want to skip part of the code, you can write some instruction to avoid the execution. And to know where to jump to, we can specify the label. As we mentioned earlier, it's like a reference for the instruction to know the address of the instruction. So we can write something like jump label, so the assembler will convert the label to some address, then the instruction will jump to this address. So there are two types of jumps. One is to jump for whatever reason, it's like unconditional jump. And another is have some comparison. If the condition is true, then the jump will happen. If not, the program will continue to run. So let's talk about the unconditional jump first. So as I mentioned, we can just write J and label. So label is defined by the user. You just tag where you want to use as a reference, then it will be a label. So when you write J label, you will jump to where the label is. And you have some other unconditional jump instruction, which is the JL and the JR. So the JL is still do the jump work, just like the J label. I do some more, the link. So the link is to store the next instruction of the current ones into one register. So this is typically bound with this JR register instruction. It will be used for function call. So in your high-level language, for example, my main function make a function call to test one. When the test one finish, it will go back to the main. So how does the program know who calls the test one? So this will be used in the return address and this JR instruction. Okay, so it's probably this is unconditional jump. So JLabel will jump to the location, and if you want it to return to where it jumped from, you will use the JL, JR to accomplish this behavior. And for the conditional branch, maybe we'll talk next time. So this will do some comparison like if and else, and they are much more complex application. We'll discuss next time. Okay, that's all for today. Okay, the slide will be provided later.